Next, we're going to talk about this new chapter itself. It's called your turning effect of force. So just remember, just recall back, your effects of the force include changing the speed, changing the direction, and changing the shape and size, right? So this changing the direction of motion itself is what we call your turning effect of a force. So more precisely, we can call it turning effect of force, a moment, or even a torque. So the thing is, in this chapter itself, you hear me say the word moment quite often, moment, moment, moment. So do take note about this. Now, so let's take a look at some of our day-to-day life where we make use of moments of a force. So the thing is, when you apply a force onto a paper itself, or onto a book, where you turn your pages, you actually have what we call a pivot itself. This is actually what we call your fixed point, or basically the part that doesn't move. Okay, it does not move. So because this part doesn't move, which part is the pivot that doesn't move? It is the spine of the book. This part of the book itself, they actually don't move. So when you actually flip your page, or for example, if you have a worksheet, it is the staple bullet. The staple itself doesn't move, so your staple is considered as your pivot itself. Okay, so do take note. And then over here, if you notice when you open the door itself at the hinge, where is the hinge or where's the pivot itself? Your pivot will be somewhere along here at the side of the door itself. Okay, so because of this, you will notice that you have a distance and you have force. So from the pivot itself, if you notice, you actually end up with this purple color turning this curved line, right? This curve over here. So this curved part is actually what we call your moment of a force. So you can see your force is the blue color one, but your purple color is your moment. So they are not the same. Because a lot of students actually make the mistake or confusion over here is that your force and your moment is the same. They are not the same. The moment is the effect of a force. So you have a force acting on an object, you can cause it to turn. That turning itself, the amount of effort you need to turn that object is what we call your moment of a force. It is not the force. Okay? There are two different values. So you can see two, your distance from your pivot and your force itself, these two are actually your factors that actually affect your moment. So if you open the door, if you try to open the door in the middle, you try to pull it, it's actually need more force to actually open the door compared to when you actually open the door at the handle. Because basically all the doors actually are designed where the handles are very far away from the hinge, right? Distance from the pivot is actually maximized. Why? Because if you have more distance, you need less force to open the door. So it's easier for you, so it won't be so difficult for you to just open one single door. Okay? And this is also the reason why if you want to close the door to your room, please be gentle when you try to close the door with at the edge, because sometimes you apply too much force and you swing it and it slam on your door, you slam it shut, your parents will scold you. Okay? Please be careful about it. All right? So this point over here, the first one, it is your of your moment itself. So keywords: force, product, perpendicular distance from the pivot. Okay. Now, yes, it's a very, very long definition itself, but ultimately the formula is just moment is F by D. Okay. Because force is in newtons, distance is in meters, you will actually have it in Newton meter itself. And what's so special is that it is a vector quantity, so you need the direction. So the direction-wise, clockwise or anti-clockwise. If you don't know what is clockwise or anti-clockwise, clockwise, you know how a clock always turns in this direction. That is your clockwise. Anti-clockwise is just the exact opposite. Okay, so the thing is, a lot of times when you solve the question itself, let's say you end up with 70 Newton cm. Okay, so if you notice over here, I can write Newton cm, right? Because for moment itself, there's no special unit like Pascal, joules, or any special like newtons, anything to kind of must use SI unit. So you can actually use Newton and cm if the question, everything, all your force is in newtons, or your distance is in cm. But if you want to play it safe, you can also just change it to Newton meter itself, just that this value will need to change accordingly. So a lot of times after you solve this, you want to say whether this is clockwise or anti-clockwise. Okay, because some schools will actually penalize marks if you only write this. You need to write this or this, the direction. So remember, it's a vector quantity. So every time you solve for a moment itself, make sure to write clockwise or anti-clockwise afterwards. Now, there's this very weird phrase on top here, to the line of action of the force. What is the line of action of the force? Weird, right? So let's go down and take a look at your force over here first. So we know that your force is down here. So what do we mean by line of action of the force? You see this line? So this line in front and behind your force. So the line that your force is acting on is what we call your line of action of the force. So remember, I told you that the pivot was one of your most important thing that you need to find, because your pivot actually, remember, it is perpendicular distance from the pivot. So number one, I need to find the pivot. The pivot, we always use the tip of the triangle itself. So over here, your pivot from the pivot, so pivot is your starting point, all the way to the line of action over here. You can see the direction, right? This is D, and you want a 90 degrees, okay? So if this is the direction itself, you can just imagine you take a finger and you move like this, right? So if you notice, this direction is like that. So this will actually give you a clockwise moment. Okay, you see that? Because you move right down. So it is going to be a clockwise direction itself. Okay? Over here, so your force don't always have to be up, down, left, right. Sometimes it can be this weird diagonal shape as well. That is why we need to say line of action of the force, because for the line of action of the force itself, if you extend it out, if you can see, this is my pivot over here. So the distance will be 90 degrees over here. So distance here. So you can see that this is now down left. Oh, sorry, down up. So this is actually a anti-clockwise moment. Can you see that? So because of this, you have an anti-clockwise moment when your force is like this. This one will be a clockwise movement. Okay? So the thing is, if you look over here, you have many forces acting on this, right? So first one, force F, let's take a look at your perpendicular distance. So you can see that it actually touches my pivot over here. So what can I say about this? There is actually no turning effect. Why? How come no turning effect? Because perpendicular distance from the pivot is 0. Now, if you notice, I keep saying perpendicular distance from the pivot, right? Why not just perpendicular distance? Or even better, just distance. Why can't I just say distance? Because perpendicular distance from the pivot is actually the keyword, the key phrase. The longer version is actually perpendicular distance from the pivot to the line of action of the force. So perpendicular distance from the pivot is actually the short form already. That's the shortest you can go. If you remove any words, you minus marks already. So minimal perpendicular distance from the pivot is 0. So therefore, there is no turning effect. So this one over here, this force F, if you notice, it also cuts through your focal point. Not focal point. It also cuts through your pivot as well. So because it cuts through your pivot, there is also no turning effect because there is no perpendicular distance from the pivot. So any force that is acting on the pivot does not produce any moment. But doesn't mean that there's no force. There is a force, it's just that it doesn't turn the object. So the classic example is, you have a door. If you have a door near you, just go to the hinge of the door. Usually it's a metal part that connects the door to the wall. If you try to open the door or close the door at the hinge, just so basically, right? For example, just now we have the diagram here, right? So if you try to apply a force here, you can never close the door. Why? Because there's no perpendicular distance from the pivot. So no matter how much force you tear, 2,000 newtons, 3,000 newtons, God knows how many thousand newtons, infinite newtons, you can't close the door. You can destroy the wall, but you can't close the door. Why? There's no turning effect. There's no perpendicular distance from the pivot. So no matter how hard you try to close the door if your force is acting on the pivot itself, there is no turning effect. You can't turn the door. So it doesn't work that way. Okay? Oh, so you don't see this. Okay, so basically over here, you have your question over here. Now, if you notice this part, assume that the weight of the rod is negligible, right? This one will make more sense in the next video itself. But for now, because there's no weight, the only force acting on here is this 25 Newton force. So number one, wherever you see a question over here, ask and find your pivot. Number two, You want to find your line of action of the force. So line of action of the force is along here, right? So what we're going to do is take your finger from the pivot and draw a straight line, or you can actually just grab your ruler actually, and you want to draw a straight line all the way to here. So this is distance D. So D is this 28 cm. Your force is over here. So you can see up, right? So this is a clockwise movement. So how do we solve this? Just now, if you actually notice the one below, we actually can. Now, to avoid any of the mistakes, right? What you can actually do is, first thing, identify, okay, my force is 25 newtons. Okay, then you can actually use 28 cm if you want, but if you are playing safe, 0.28 meters. So using this force times distance, write the formula down. A lot of you don't do this. So write the formula down, and then you can actually solve accordingly. Now you can leave it as Newton cm or Newton meter, but don't forget the most important thing of all. You want to mention the direction, because a lot of students will skip this part. Why? Don't forget, this is 2 marks. Your formula and correct answer is 1 mark only. So where did the second mark go? It is the clockwise direction that they want to find. So if you don't write the direction, you will actually penalize marks. So you need to be very, very careful about this. So do take note, okay? So if the question gives you Newton cm, then you should write 700. If the question gives you Newton meter, then you should write 7.0. Okay, don't write 7 up. Always put in 2 or 3 SF. Okay. The next one over here, you have a force acting on the rod itself. Always take your finger or use a pencil, draw your line of action of the force. You'll notice that, hey, my force is acting on my pivot over here. So as a result, there is actually no moment, because moment is F times D, but your distance D is 0. So because it's 0, you have no force. Remember, horizontal force, you are finding vertical distance. Diagonal force, diagonal distance. Okay? Now, for all of this down here itself, you want to find the moment of each force. So before you start solving anything, always identify your pivot first. So after you found your pivot, next thing you want to do is find the line of action of your force. So let's do them one by one. So you can see each and every force acting on the same object. All of them will have their own moment itself. So this is very, very important because later we'll be solving multiple moments at one shot. Okay. So first thing you want to do is from the pivot, I will draw and find the distance over here. So this and this. Okay. So if you notice, it's meter, 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 Newton, Newton, right? So I can just use exactly. So moment is F times D. I'll use 15 times 0.30. I'll end up with 4.5 Newton meter. And what direction is this? This is left down like this. This is anti-clockwise. Okay. Next one, I'll use a different color. So your force over here will give you a force like this, right? So the thing is, because it's acting on the pivot itself, there is actually no distance. So D Newton here, distance is 0, this is 0, and so this doesn't affect any count. Doesn't affect the moment. It doesn't turn the object. Okay. Last one over here. If you have force, if you extend it out, you will have a perpendicular distance, right? So where's that distance itself? Is from here all the way down. So this is for this guy. Okay. So over here, your moment is F times D. You have 25 and 0.25, right? And 6.25 Newton meter. And don't forget, what direction is this? This is actually, we're going down and left. So down and left, we actually have this. This is actually a clockwise moment. So now, extra side note. Now we have what we call your total moment or your resultant moment. So it's kind of similar to your force. So the resultant moment itself, we're going to take big minus small. So we actually have your clockwise moment minus your anti-clockwise moment. Okay, so we have 6.25 minus away 4.5. We are now at 1.75 Newton meter, and this is going to be clockwise. So what do we mean by this over here? This means that overall, my bent bar over here will actually rotate clockwise. So yes, even though I have this anti-clockwise moment on the left, because of the total clockwise moment itself, which is this green one minus the red one, which will actually cause my object to turn 1.75 Newton meters clockwise. So we actually turn my object in this direction, clockwise direction. Okay, so that is why we need to solve all your moments, and you solve like this. Okay, so this is when you have different clockwise moment and anti-clockwise moment. So in the next page itself, where we learn about principle of moments, if they are the same, you will remain stationary and what we call equilibrium. So this word equilibrium over here, there is actually two things you can happen. Number one, resultant moment is 0. Number two, resultant force is 0. So make sure that when you know when the object is stationary or in equilibrium itself, what you can say is up equals to down, or left equals to your right. Correct? This is your moment, resultant force, right? Newton's first law. And we also make use of this where your clockwise and your anti-clockwise moment is the same. Clockwise moment, anti-clockwise moment, they are the same. They are balanced. If you are stationary, if you are equilibrium. So below here, this one, very, very, very important. Memorize. Okay, must memorize this. So the thing is, for this one over here, that is actually worth 2 marks. And as most explanation question goes, if it is worth 2 marks, it is usually 3 points. So number one, when the object is in equilibrium, some students will miss that out. Total clockwise equal to total anti-clockwise. Okay. And last but not least, a small little detail that causes students to lose marks is that you must use the same pivot. If you have 2 or more pivots itself, we only focus on one of them. Okay, we only choose one pivot and we will rotate about that same pivot itself. So sometimes you can have more than one pivot itself. It's not really a difficult part. But don't get confused. Your pivot is the point that doesn't move. Okay, so you will end up using this formula over here to solve for your unknown. Now, if you draw a line over here, basically the part above here is your principle of moments where clockwise equals anti-clockwise moment. Everything is the same. No problem, no issue. Then the one below here is if they are not the same, my object will rotate. Which direction will it rotate? If your clockwise is bigger than anti-clockwise, you will rotate clockwise. If your anti-clockwise is bigger than clockwise, you will rotate anti-clockwise. That's what it means basically. Okay. Now, if you notice over here, one thing special about this setup is if you notice the top part of your scissors, okay, treat it as one single object, okay? Ignore the bottom part of your scissors, all right? Now, you can see that your pivot is down here, correct? Your line of action will be over here, 90 degrees, correct? So this is your distance D, you have a force F downwards. So what happens, this will give you a clockwise moment, correct? So what happens is, this clockwise moment will cause the yellow color scissors, right? The top part, the whole entire thing will rotate clockwise, which means this part will also rotate clockwise. Do you see that? Basically, it's like your ruler, right? If you flick it, it's going to rotate in a certain direction. The same thing, if it actually occurs for both the top and the bottom as well. So basically, for the bottom part, the perpendicular distance is the same, but now if you notice, the bottom part is actually an anti-clockwise moment. So on top here, you actually have a anti-clockwise moment as well. So can you see that? That's how you actually use the scissors to cut something. So because the scissors is actually moving, this is not principle of moments. Okay, this is not principle of moments. This one is this part over here. My clockwise moment here, and therefore I have a clockwise moment here. I have an anti-clockwise moment here. I have an anti-clockwise moment here. This one, because my scissors is moving, I'm snipping something. So because of this, this is not principle of moments. Principle of moments must mean that your object is not moving. Okay, which in this case, this one is not moving. So you can just imagine you standing here, holding it up. Okay, so what happens is, where's my pivot? Pivot is right over here. This is my pivot, and each and every one of them will have their own perpendicular distance. Okay, so this one will give you a clockwise moment. This one will give you a anti-clockwise moment. Okay. So what can you say here? Because my wheelbarrow is actually not moving, we can say that we can use principal moments where your clockwise moment is equals to your anti-clockwise moment. Can you see that? So because of this, this is your principal moments itself. So normally when you have two or more forces, this is how you solve. Now, normally for this kind of question itself, usually it's a screwdriver, a hinge, a screwdriver, like a spanner or something like that. Usually it won't really be a scissors itself because scissors is a bit complicated. Something usually will be more straightforward itself. Okay, so because of this, if you move, you don't use principal moments. If you don't move, this is your principal moments itself. So this one is just for me to break it down to you itself. So over here, if forces are balanced and moments are balanced, this one is equilibrium. That's why it's in green. Now, if your forces are unbalanced itself, this is actually your resultant force. It's M times A. So because of this, you either away, move in a certain direction itself. Now, this one over here basically means that your resultant moment is not zero. You will either have clockwise greater than anti-clockwise or anti-clockwise greater than clockwise. Okay, so in the end, you rotate in a certain direction itself. This one, last but not least, this one is not in your syllabus. This is uni level. Okay, the difficulty is only seen in uni. I took this in uni. It was very, very difficult. So yeah, this one you won't encounter this, hopefully, for the IP schools. Hopefully you all don't have this weird part over here. It's very, very complicated. Okay, so most of the case we will actually do the green color one and the one on the right. So this is your forces dynamics chapter. This is your moments chapter on the left. Okay, so usually they are kept separate unless it's a 10-mark question. Now, work example over here. So you can see over here, number one, I have a mass, 20 kg, and you want to turn the nut. Okay, so because you want to turn the nut, the word turn, it must be moment already. Okay, so this is me trying to tell you this is not force, because a lot of students see mass, oh, for mass, it must be force already. F equals ma. No, it's not. Okay, so now the question is, I have weight over here. Remember, this is not mass, this weight. So it's W equals mg because we need a force to turn, to produce the turning effect, to have a moment. So where's your pivot? Pivot is right over here. So I'm gonna have a perpendicular distance over here with my line of action like this. So you can see it will be a clockwise moment. So now, if you turn the nut, you will notice that the nut will actually turn in this direction itself. So this moment is actually the same. Can you notice that? So because the moment is exactly the same, we actually can say that this clockwise moment and this clockwise moment will be exactly the same. So let's solve. Okay, so because we know that you are going to move the nut and the spanner both at the same time, there will not be a, this is not principle of moments. Okay, this is like the scissors example just now. So let's take a look. We can solve them separately first. So number one, if you want to solve for your moment, you first need force, right? Moment is F times D, right? So let's solve your force first. In this case, it is weight. Okay, so weight is M times G. What is weight? 40, right? No, it's 20. So it's 20 times 10, you have 200 newtons. Okay, and because if you notice the distances in the diagram itself is all in cm, I'm not going to change it. I'm going to leave it as it is. Okay, so I have this. So your moment itself is just your weight times distance, or force times distance, depending on how you see it. So it's 200 newtons and 25.0 cm itself. You actually end up with 200 times 25. You end up with 5,000. And don't forget, this is Newton cm. Okay, because it's 5,000 Newton cm itself, this is your clockwise moment. Okay, don't forget to write the direction, because if you miss out the direction, you might lose marks. Okay, so now we know that your clockwise moment is F times D. So just now, all of this in red color. Okay, let me just bring this down slightly. So all of this over here is due to the mass. Okay, so this one over here is due to your nut. So the clockwise moment itself is 5,000, right? We want to find how much. force unit, and then the distance given is 0.80. So force is just 5,000 divided by 0.80. So how much it is? You actually get 6250 newtons. Do remember, this is force. That is why I always tell you all to write your symbols nicely and properly, including the formula itself, because you can just check, oh, force, newtons. If you just throw in numbers itself, something gets very, very confusing, because for this chapter itself, you can actually deal with up to 5 moments in the same diagram itself. So if you don't label which is which, it's going to get confusing really, really fast. Okay? So because of this will be our force, and that will be the direction that we have, the amount of force you need. Okay? All right. So next, over here, your wheelbarrow itself. Now your wheelbarrow, if you notice over here, have a weight, 250, and now you have an extra 40 kg mass, which means you have a weight down here. And this is M times G. You actually have 400 newtons over here. So now you actually have 2 downward force and you have 1 upward force over here. So in total, you actually have 3 different forces acting on your object. And where's my pivot? Pivot is right over here. So let me just color code it so it's easier to see. You have your first distance here, you have your second distance here, and you have the last one, which is all the way to the right. Because a lot of times this questions will actually trick you. You can see over here, they give you 30, 40, 50. If you write 30, 40, and 50 for the distances, you are wrong. Why? Because the distance from the pivot to each of the forces is 30, 70, and 120 itself, respectively. So you need to be very, very careful. So because you can see, right, I will have a clockwise, I'll have a clockwise, and I'll have a anti-clockwise over here. So because of the different directions itself, you actually will have 2 clockwise and 1 anti-clockwise. So because of the different directions, I will need to use principal moments because this is not moving. You notice that? It's not moving at all. So let's use, so how do we write principal moments itself? So before we solve principal moments, because of the working itself, you want to write W is M times G. 40 times 10 is 400 newtons first. Okay, clear out the necessary steps first. Everything else, cm, Newton, everything is good. So now, by principle of moments. Yes, you need to write the whole thing out. There's no shorter way. Total, and if you notice, because we are trying to find F will give us anti-clockwise, so we write anti-clockwise moment here. We cannot write short form the very first time we write this. But if you're doing another question after this, you can write short form. But most school paper itself, we are only dealing with 1 moment question in the whole paper. So total clockwise, total anti-clockwise. This is worth 1 mark. If you don't write this, you lose marks already. Okay. Next step. Your force times 120 cm and your weight 250 times 30 cm plus your 400 times 70 cm. Now, if you notice, I put brackets for each, right? Why is that so? Because this is just a reminder to yourself. This is 1 moment, F times D. This is 1 moment, F times D. This is 1 moment, F times D. Each and every single one of them will have F times D each. 3 forces, 3 moments. So now all we need to do now is solve for F. Okay, so we can solve it. 250 times 30 plus 400 times 70, end up with 35,500. And if you divide by 120 over here, you get a weird long number, 295.83. If your school uses 2SF, it will be 300, but I'm just going to use according to most students, which is 3SF. So 296 newtons 3SF over here. Okay? If you're IT school, most likely you guys will use 2SF. So double check. Why 2SF? Because the 1 to 12. Okay, so we use 2SF here instead of the longer one. All right, all good. This is how you solve. Now on the side note, let's draw more cloud. Okay, now if you notice over here, because it's not moving, your resultant force by right should be 0, right? So your total up equals to your total down. Make sense? So, but then if you go and notice, your total up is just about 300. Okay, let's use 300 for the one below here. 300 2SF. Okay, to simplify things first, this one is just to show you all. This is 250 and this is 400. They don't match, right? So there must be another force. And what is this force itself? It's actually your normal contact force here. Because don't forget, you are touching the ground. So there is actually a normal force somewhere supporting this wheelbarrow. But the thing is, even though you have 350 newtons of normal force, what happens is there is no moment. Moment is F times D, right? But the thing is, because my force, my 350 force is acting on the pivot. Do you see that? It's acting on the pivot itself. So because of this, you actually don't have any kind of moment. So this normal force does not affect my turning effect. It doesn't affect my moments, doesn't affect my principal moments. But is there a normal force? Yes, there is a normal force. It's just that this normal force doesn't cause any moment itself because it's acting on the pivot. So yes, there is still a normal force. They are not balanced without this normal force. So if you need to draw a free body diagram itself, you have two weights, one normal and one applied force. Okay, so just be careful. This is more of a side note, but it is something that your school can actually test you on. So do take note about this. So in the next video, we actually talk more about what we call your center of gravity. Okay.